Hey guys, so now we're moving into a new section on nuclear, and this is one of my favorite chapters because it really talks about things that we don't discuss on a normal basis, but it's really important for chemistry and for nuclear and nuclear bombs and things like that, and just understanding what potentially could happen in the future if we don't keep abreast about what's happening with other countries and how their nuclear chemistry developing is going on. So we're going to focus on a lot of different things this year in nuclear chemistry. Okay, so the first thing we're going to talk about is what really is radioactivity. So now remember, anything in red is what you need to copy down in your notes, okay? Because when you get your study guide, this is what's going to help you answer your study guide, or the things that are highlighted in red. So this is in the boxes that you're going to fill out, okay? All substances are made of atoms. So we just got done talking about atomic structure. So we know a lot about atoms. These have electrons, which we talked about before, around the outside, and a nucleus in the middle. The nucleus consists of protons and neutrons, right? So we've been talking about this in detail for several weeks. Now, atoms are almost entirely made of empty space. Remember how we talked about Rutherford's gold foil experiment, and he concluded that the atom is mostly empty space with a positive core, and then later we discovered that it's not just protons in there, that neutrons are also part of the overall mass of the atom, okay? Now, in some types of atoms, the nucleus is unstable, all right, and will decay into a more stable atom. This radioactive decay is completely spontaneous, okay? The energy that is released from the nucleus of the atom is radiation. Now, when they first started studying this, they didn't know at all that what this energy, this radiation that they started developing, was going to cause them harm, okay? It wasn't until their deaths that they realized that this, in fact, was stuff that you need to have protected because it was causing cancer and things like that, but they didn't know that till after the fact, okay? Now, in the late 1890s, okay, scientists noticed, all right, that some substances spontaneously emitted in a process they named as radioactivity, okay? So this is how, so they actually gave it the name radioactivity. That's in the 1890s, that's when it first started to come about. Now, there was a man by the name of Henry Becquerel, okay? He was one of the pieces of evidence for the fact that atoms are made of smaller particles came from his work, okay? He discovered radiation, the spontaneous disintegration of some elements into smaller pieces. So now we talk about splitting of the atom, but you guys really don't go in depth into that. So you don't understand what that whole process is talking about. And Henry Becquerel's research really led people in that direction and started thinking about, okay, we can split an atom. And that's how the development of the hydrogen bomb came about, was from his work. Now, other pieces of evidence for the fact that atoms are made of smaller particles came from the work of Marie Curie. She was the first female scientist to win the Nobel Peace Prize. She was also very, very influential in the knowledge of radiation, and it actually ended up causing her death years later, okay? She discovered two elements, polonium and radium, okay? Both radioactive elements in 1898. Now, it is said that Marie Curie's clothing that she wore when she did all of her research in the lab is to this day still radioactive. She used to carry samples of polonium and radium in her pockets of the different dresses that she would wear, the lab coats that she would wear. She would carry them in her pockets when she was walking around the lab. And it's interesting because she didn't know at that time that that radioactive material could cause cancer. And so they actually have her clothing on display, but it's actually encapsulated in a box, a lead box, or maybe it's a plastic box, some kind of plexiglass where the particles can't get out. But it is encapsulated in there so that people could go by and view, but her clothing is still radioactive to this day. So I find that very, very interesting. Now, there we go. The atomic disintegration theory of radioactivity is published by Rutherford and Frederick Soddy. Now, we heard a little bit about them earlier in atomic structure when we were talking about the theory of atomic structure. So they also had a lot of involvement in the development of radiation and radioactivity. Okay? Now, what really is radiation and radioactivity? Okay? It's when an unstable nucleus decays. There are 3 ways that it can do this. Okay? So it releases particles when this happens. When you have this radioactive decay, it's going to emit certain particles depending upon the material that you're dealing with. So the first one is called an alpha particle. Now we use this symbol alpha, okay, as an alpha particle. Then you have a beta particle and a gamma ray. Now on Friday, you read an article called The Radium Girls, okay? A lot of that material that you read for radium was solely focusing on alpha particles. Now, what's so interesting about the story of the Radium Girls, and I'm going to put a video on the slideshow to kind of show you about the Radium Girls, is when they were actually in these watch factories, they would lick the brush, right? They would lick the brush and then they would use that paint. And all the scientists told them that this paint was not going to harm them. So they would dip it on their tongue to get a point, and then they would paint these watch dials so that the numbers would glow in the dark. So they were ingesting this radium. Didn't know anything was wrong. Some scientists knew, but they kept it under wraps because they didn't want anybody to know. And so what happened was they kept ingesting it. Well, when we're going to find a little bit more out about alpha particles, they're not as dangerous because you can actually block an alpha particle with a sheet of paper. Well, when you ingest it, it doesn't leave your body, okay? So that's something interesting, and we're going to talk a little bit more when we get to the slide on alpha particles. I'm going to give you a little bit more information about the Radium Girls and why, in fact, they actually were dying because of this radium poisoning. Okay, so alpha particles, remember, whatever's in red, you copy down. Alpha particles are made of 2 protons and 2 neutrons. So they actually reference it as a helium atom, okay? This means they have a charge of a +2 and a mass of 4, okay? We write them as a particle or as a helium atom. So you might want to copy that down. This is an alpha particle, which we've referenced as a helium atom. So this right here, this helium atom, is what I want to make sure that you write down and you have, because we're going to use this a lot when we start talking about nuclear equations and reactions that we're going to talk about here in a few minutes. Now, alpha particles are relatively slow and heavy. They don't move very fast, and they have low penetrating power and can be stopped by a sheet of paper. So if I move over here and I pick up a sheet of paper and somebody shoots an alpha particle at me, I can hold it up like this and stop that alpha particle, right? I can block it. So your clothing and your skin would also block alpha particles, okay? Now, because they have a large charge and alpha particles ionize, they pull electrons from other atoms strongly. Now let me give you a little bit more background information about these alpha particles. Once you ingest these alpha particles, they stay in your body because there's nowhere for them to go, okay? So that's why it was so dangerous when these factory workers were ingesting these radium compounds, because once they got it in their system, it stayed there. Now, if you look at radium on the periodic table, it's actually in the same column as calcium. And so why is that interesting? Well, because elements that are in the same column have the same types of physical and chemical properties. So what ended up happening is radium is not supposed to be in our body. So when they ingested this radium, the body and the brain thought that the radium was calcium. So what ended up happening is the radium was blocking any calcium from bonding to the bones within the people's body. So they started getting holes in their bones, they started getting these large growths on their face and things like that because the brain thought that it already had enough calcium. So their bones started breaking, they were having all kinds of issues. One guy had a hole in his head because they also used to do radium therapy where they would have people drink radium, okay? And it was known as Radithor, and they said it had healing powers. So they would allow these people, the doctors were prescribing this Radithor for people to drink, and so this one guy ended up with having these holes in his skull because of the radium poisoning. So all of this was all around the same time where we had the Radithor, where we had these radium compounds in the paint. And so all these people were getting really, really sick because they didn't understand that this radium was poisoning them. Okay? And it simulated, like I said, calcium because it's in the same column as calcium. And so there was a big lawsuit. People were sued. These people ended up dying. But eventually their families did get a settlement, but not very much money. But so they say to this day, and actually several years ago, I'm actually from New Jersey, so I actually went to Orange, New Jersey, where these people are buried, and I had a Geiger counter. And if you go across their grave with a Geiger counter, it is said that they still emit alpha radiation from the grave. And that's actually true, because if you go over there with a Geiger counter, it will detect alpha particle radiation if you have the right kind of Geiger counter. And so I've actually done it, and it did give off some radiation. So think about this. These women were, you know, when you read the radium article and you saw how long ago that was, these people are in a casket, buried in the ground, but yet their bones are still giving off radiation. And we're going to find out why that is a little bit later when we talk about the half-life of radioactive material. That's going to give you some idea about how long it takes for some compounds or some elements to actually decay half of their life. So that's something else we're going to talk about later. So a lot of info about alpha particles. Okay, beta particles are a little bit different. They're actually more dangerous than alpha particles. They have a charge of a -1 and a mass of 1/2000th of a proton. Okay, so it's about the size of an electron. This means that beta particles are the same as an electron. Now when you write a beta particle, it has a B with a negative charge. But when we write them in a nuclear equation, we're going to write them more like this, okay? Or because they're the same as an electron. And a lot of times I actually write an E here instead of a B for beta. But you'll put a 0 at the top because it doesn't have any mass that is going to affect, right? So we talked a little bit about this before, about how electrons have mass, but their mass is so small that it's not going to impact the mass of an atom. Okay, so that's why they put a 0 here. They're not saying that it has 0 mass. They're saying that the mass is irrelevant in the nuclear equation because it doesn't affect the mass of the atom because it's not large enough. And then it has a -1 charge. So beta particles are fast and light. Okay, and that's not a good thing. You know, it is for a person to be fast and light, but it's not good for radiation to be fast and light, right? So beta particles have medium penetrating power. They are stopped by a sheet of aluminum or plastics. Okay? They are stopped by aluminum or plastics. Beta particles will ionize atoms that they pass, but not as strongly as alpha particles do. Okay? All right, moving on. Now, the real dangerous ones are gamma rays. And I know you've heard of this because this is when you get an X-ray, they talk about gamma radiation, right? That's not good for you. And those people that wear those badges that take the X-rays, it's actually recording the amount of gamma rays that they're being exposed to every month. And they have to turn those badges in and they have to record it. And there's a certain number that they have to fall within a range. And if they're outside of that range, then they can't do X-rays for a while. Someone else will have to go in there and do the X-rays just because they're trying to protect the person from gamma radiation. Okay? So they are waves and they're not considered particles like alpha and beta. Okay? This means they have no mass or charge. Okay? So they're extremely small. Gamma rays have high penetrating power. It takes a thick sheet of metal, okay, such as lead or concrete, to reduce them significantly. So if you've ever had X-rays done at the dentist and they lay that big apron on you that's kind of heavy, the reason they do that is because that's a lead apron. So what they're trying to do is when they X-ray your mouth, they're only putting the gamma around where your mouth is and they're protecting the rest of your body from the gamma rays, okay? Because over time, that can be dangerous. Same thing when they take an X-ray, they go into that little concrete box and take the picture because they're trying to not get gamma radiation and stand out in the open. They're trying to block those gamma rays from getting to the person who's doing the X-rays. Okay, so that's why they stand behind those little concrete boxes when they do the X-ray, is because concrete and lead will block most, not all, but most gamma radiation. Okay, some will still get through. All right, so We don't find pure gamma sources, so it's just not out there. Gamma radiation is not just sitting out there, okay? They're not pure forms of gamma radiation, okay? Gamma rays are emitted alongside alpha decay and beta decay, okay? Strictly speaking, gamma emission isn't radioactive decay because it doesn't change the state of the nucleus. It just carries away the energy, okay? So you don't have gamma equations, you have gamma rays as a byproduct of an alpha or a beta decay. So summaries, let's summarize this. So here you have your alpha particle, right? So when an alpha particle is emitted, here you have a sheet of paper, boom, it's blocked, right? Now you have beta. Beta is going to go through the paper, but then you have aluminum that's going to block a beta decay. And then finally you have your byproduct of your gamma ray that's going to go through the paper, through the aluminum, and the lead or concrete is what's going to block most, but not all gamma radiation. Okay? Now, I'm sure before you've heard, there are also some other particles that are byproducts of nuclear reactions. And we're going to talk more about those a little bit later. But here you have a neutron that causes some things when we're going to talk about fission and fusion. And then you have a positron, which is a positive electron. You also have a proton, usually referred to as hydrogen 1, and then other elemental isotopes. Okay? Now, we're going to get to the part that we're going to be doing our nuclear reactions or our nuclear equation problems, dealing with alpha and beta radiation. So isotope notation includes additional information about an isotope. In addition to the chemical symbol, the mass number and the atomic number are included. This allows information about the nucleus to be determined. The isotope notation for an atom of uranium-238 is this. Now this you saw in the last chapter, right? This is the isotopic symbol, where you have the mass number here and the atomic number here, and then you have the chemical symbol. All right? So, when we're looking at this, okay, the mass number is 238. This is the sum of the protons and neutrons in the nucleus. The atomic number is 92. This is the quantity of protons in the atom. It also leads to the chemical symbol for the isotope, which is uranium, U. Okay? Now, how does nuclear decay of these reactions occur? Some elements are naturally unstable. Okay? They tend to undergo alpha decay or beta decay to become more stable. They may take several steps in order to achieve this, thus we observe decay chains, also known as a series decay, for most radioactive elements. So your radioactive elements are going to have a decay involved with them, okay? And this is an example of a radio decay series. Now, I'm just going to show you this picture, and we're going to talk more about this in detail when we talk about the half-life, okay? So right now I'm just showing you mass number, atomic number, and these are what radioactive elements actually decay into when they give off a beta particle or when they give off an alpha particle, okay? And we're going to do some reactions with this in a moment, okay? All right, so alpha decay. It is one process that unstable atoms can use to become more stable, okay? Here's a large unstable nucleus, then you have a smaller, more stable nucleus, and then here is your alpha particle that's broken off of the original sample. So now you have a new element, and then you have your byproduct of your alpha particle. During alpha decay, an atom's nucleus sheds 2 protons and 2 neutrons in a packet that scientists call an alpha particle. Okay? So here's what's actually happening. Since an atom loses 2 protons, 2 neutrons during alpha decay, it changes from one element to another. For example, after undergoing alpha decay, an atom of uranium with 92 protons becomes an atom of thorium with 90 protons. The reaction below is written. So, in a reaction, you're going to get this part right here. And I'm going to tell you it's alpha or beta decay. In the problem, I'll say this undergoes an alpha decay. All right? Meaning that a helium atom is going to be stripped off of uranium-235. Now, how do you figure out what's going on? Well, when you strip something away, you're subtracting it, right? So every time you do an alpha decay, you are going to subtract a helium atom from the original sample. So here's how you would do it. Just look at the top numbers. I'm going to say, what is 235 minus 4? That's going to be 231. What is 92 minus 2. That's going to be 90. So what I do in an equation like this, I'm going to write my helium atom because I know it's an alpha decay. Anytime they say alpha decay, this is the alpha particle. This is what you're subtracting off of the original sample. So once I subtract that, I'll have 231 and I'll have 90. Now this right here, this 90, that's the number that's important for you. Because then what you're going to do is you're going to go to your periodic table and you're going to look for element 90. And when you do that, this is how you're going to reach the chemical symbol, which is thorium, which is TH. So this is how I got TH in the problem. Don't ever look at the mass number to find the symbol, because remember, we're dealing with isotopes. So on occasion, it's not going to be the same mass, but it will always be the same atomic number, right? Because the atomic number is what identifies the element. So anytime you have a sample and you undergo an alpha decay, you are going to subtract off a helium atom from the original sample on the left side. You'll draw your arrow, you'll draw in your helium atom, and then you will draw in your sample of the byproduct after subtracting the helium atom. Okay, after subtracting 4 from the top and 2 from the bottom, it will give you your new element, your byproduct of the alpha decay. All right? Now, beta decay is a little bit different because you're dealing with an electron now, which is negatively charged, instead of dealing with a helium atom, which is positively charged. Okay? So during beta decay, a neutron turns into a proton and an electron. The electron emitted is called a beta particle. Okay? Now, so when this happens, when this beta happens, this is what you're going to have. So if I have hydrogen 3, which is an isotope of hydrogen 1, that means I have a mass number of 3 and an atomic number of 1. If I subtract off an electron, which is a beta particle, from the sample, so this is my beta particle right here, and I probably should have written that in the other order. Basically, what you're doing here is you're subtracting. So what is 3 minus 0? That's going to be 3, right? Okay. What is 1 minus a negative 1? Well, that's a positive 1, right? So that becomes 1 plus 1, which gives me 2. So now my symbol is going to be He for helium, but look, does it have helium-4? No, because helium-4 is an alpha particle. So a byproduct of a beta decay of hydrogen-3 is going to be helium-3, okay? So let's review this again. When you have a beta particle and you subtract and you emit a beta particle, you are stripping the beta particle off of the original sample. But remember, the neutron actually splits into an electron and a proton, and that proton adds to the original sample. So it's not really like the alpha particle where we subtract it off. We are subtracting the electron off, but then we're adding the proton, and that's why you have a higher atomic number here and no difference in the mass. Okay, so the mass stays the same, but the atomic number changes because you're adding that proton, which in turn makes it a helium from a hydrogen. Okay? So let's look at what's happening here. So in a alpha emission, you have your original sample. You subtract off a helium atom, and then you're left with whatever's left here. So whatever you have, minus 4, and the atomic number, minus 2. And then you have your helium atom. In a beta emission, you're taking an electron and you're subtracting the electron, which in turn does nothing to the mass number, but changes the atomic number and increases it by 1. Okay? Now, there's positron and electron capture. I'm showing you what these are, but we are not covering this in our chapter. So you are not going to be responsible for knowing how to do a positron emission and an electron capture. I'm showing you that they're there and that they exist, but we are not covering that in this section. The only two nuclear equations that we're going to discuss and have work on is going to be alpha and beta emission. Okay? All right. So here's another example. All right. So if I have uranium-238, once again, I subtract off a helium. I have 234 and 90 for thorium. And then for my beta emission, if I have iodine-131 and I do a beta emission, then I have 131 minus 0 is still 131, and then 53 minus a negative 1 is going to add 1. So that's going to become 54, which changes my element from iodine to xenon. Okay? So that's the difference. All right, so last slide that we're going to go over. Okay? And let's try to do an example of this. Okay? Now, let's see if we can figure out what decay type occurred in this example. We have radon-222, which is the mass number, with an atomic number of 86. If I look over here, I now have polonium-218 with an atomic number of 84. Just by looking at this, I can see that 222 decreased by how much? 4 when it decreased to 218. 86 decreased by 2, right? So the only thing I can assume there is that this was an alpha particle, 4 and 2, and a helium, and this type of decay is an alpha decay. All right? Looking over here, I had thorium-228 with an atomic number of 90. Then I look after the reaction, and I have the same mass number, but instead of thorium, I now have palladium, 91. So I increased my atomic number by 1. So that right there should tell me that I emitted a beta particle, right? Which is 0 minus 1 with an E for the electron. And the decay type would be a beta decay. All right, so now you guys are going to have a worksheet on nuclear equations. If you have questions, please email us. We will help you. These are a little complex. We might even later send a video out through Google Classroom which shows some examples of how to do some of the nuclear decay. All right? Hope you have a good day. Take care.